All right, so we've talked about points, and let's go ahead and talk about one dimension up and look at directions. And so in this module, we're going to look at how we determine crystallographic directions. All right, so just like we have point coordinates in Cartesian, coordinates, uh, with directions, these are the same thing as vectors in from your math class. So all a crystallographic direction is a vector, but we do kind of make the caveat that it's a vector, but we're only talking about a vector within the unit cell. So, we are talking about a given direction, and so it doesn't matter that it kind of stops within the unit cell, but it's easier for us to draw it if it's within the unit cell. So that's kind of why we say within. And so all this vector is defined by, like a vector in your Cartesian coordinates, is by the endpoint minus the initial point. Right? So we define it based on points. And so that's why we need to do the crystallographic points first. And so we do it that way. So the easiest way to do this ourselves is, if we're trying to determine the direction of this vector here, is to put the initial point at the origin. And we'll see why that is in a second. So we take the endpoint, initial point, and that gives us the direction. So in this case, our endpoint, in this case, if we do the same process we did before, this point is 1, 1, 1, as you see over here. And then the initial point is 0, 0, 0, because it's the origin. So it makes it easy because if we define a vector or a direction by endpoint minus initial point, if we use the origin, the initial point is always 0, 0, 0. So our endpoint translates to our direction. So when we subtract those two, my direction indices are 1, 1, 1. And if you're wondering about the indice part here, indices just refers to the numbers. So 1, 1, and 1 are all the indices that we have. So that's just a fancy way of talking about the numbers. And so that's how we define a direction. But we want to have a very common notation that we all use. So in crystallography, when people talk about crystals, particularly in the materials field, the way we write a direction is very specific. So just like points, we don't use commas. We never use commas. And we put those indices within square brackets, as you can see here. So you might ask yourself, why? Why the square brackets? Well, the square brackets are just something to tell us, if I look at this without even knowing about all the other stuff, I can say, oh, these are square brackets, so this is going to be a direction. And then the indices are 1, 1, and 1, right? So it's just a common notation that everybody uses, and so that you know exactly what you're looking at. I see square brackets, I know that it's a direction. All right, so let's kind of formalize the process that we use. And so in all of these kind of crystallographic topics, I'll kind of formulate a procedure for you. Our textbook, Callister, also has procedures, and you'll probably notice that they're quite a bit different than the ones that I'm using. So you can get the same answer multiple different ways, but this is the procedure that I prefer and I think is easiest. So if you don't agree with me, obviously feel free to look at the book and use the procedure that they use as opposed to mine here. So just a heads up on that. Okay, so let's say we have a given direction and we want to determine the indices. We want to write it down, right? So the first step that I'm always going to have you do is move the vector so that it passes through the origin, right? So this isn't passing through the origin, so I'm going to move it so that it passes through. That's the first step. And then I'm going to read off to projections in terms of the unit cell dimensions. So basically, this is the step we did with points, right? Determine the endpoint of that vector, and that gives us our indices. So then the other aspect here is that we haven't seen it yet, but another part of the notation for directions is that you want to have the smallest integers possible. So you don't want to have the direction 2, 2, 2. Instead, you write that as 1, 1, 1. So you always kind of reduce to get the smallest integer values that you can once you have those projections. And then again, you enclose in square brackets and no commas. So the generic form here is UVW, where UV and W are those fractional projections in terms of A, B, and C. So that's how we write a direction. All right, so let's go through the example here that I showed you in the previous slide. So step 1, we are going to move this line, this direction, right? Because this one passes through the this point over here, but not the origin over here. So what we can do is, on a piece of paper, we can kind of, just redraw it going through the origin. And so basically that's what I've done here. I've just switched it over. The other way that you can do this, instead of moving the line, is to actually move the origin system. So if you want to redraw the origin system, the coordinate system, starting with this point, you could also do that as well. So feel free to do it whatever way you want. Either move the direction or move the coordinate system. But that's what I have here. I've done it. I've moved it. So now that this is at 0, 0, 0. So that's step 1. Let's look at step 2. We're going to read off projections in the X, Y, and Z directions, which correspond to the fractional amounts of A, B, and C. So the way I like to do this is to make myself a little table. And I put X, Y, and Z up here, and I basically write down my projections for each. So I see that this direction is on the back face, the YZ face. And so it's not projected at all in the X direction here. And so that is going to be 0A because it's not projected in the X direction. So then we go to Y. So for Y, the projection, it runs the length of the Y direction. So that is 1, right? So it goes all the way, it touches this edge. And so that's 1 length of B. So 1B, right? Now, or the projection, if you project it down to the y-axis, is 1. And the last part, in the z direction, the projection is going to be 1/2, right? Because we basically, from this point, go up 1/2 the length. And so that would be 1/2 c. So those are my projections. All right. So step 3 was to adjust to the smallest integer values. So right now I have 0, 1, and 1/2. Well, 1/2 is not an integer, and we always want to have integers. So what we're going to do to get integers, the smallest, is the way we could do that in this case is to multiply everything by 2, right? So if I multiply everything by 2, this is still 0, this is 1, or sorry, this is 2, and then this is 1, right? So I've got 0, 2, and 1. And the reason we can do this type of manipulation is if you think about it, the direction here, all we want to describe is the direction. The length of that direction doesn't really matter, right? Because this direction keeps going in space, right? But we're only describing it in a unit cell, which is why we have these. So to get integers, we sometimes have to multiply or divide. And so the last part here is enclosed in square brackets with no commas. So we take our 0, 2, and 1, and we write it in here. And that gives us the 0, 2, 1 with square brackets around it.